Today we're going to start Unit 2, which is Scientific Measurement. If you were present in class today, I have this student document that's also attached to the notes that goes with the slides. If you were absent and you're watching this video from home, pause the video, go back into Google Classroom, and if you look at my post for notes, there's also a doc. So make sure you open up that doc as you watch this video, and we're gonna fill that in as I go through the slides. So in class today, we did a measuring activity at our table with some special rulers. So if you're watching this from home, you're going to skip the first little chunk of the student document. So you're not gonna measure the lines under ruler A, ruler B, and ruler C. However, we can answer these analysis questions. So on your student document, kind of look halfway down the first page, analysis questions. So what distances can you be certain of on ruler A? So if we look at ruler A, we have a mark at 0 centimeters and 100 centimeters. So we can be certain of distances of 0 and 100. Number 2, what distances can you be certain of on ruler B? So here's ruler B. There's a line every 10 centimeters. So we can be certain of a measurement if it's in any of the tens place. So 0, 10, 20, 30, 40, and so on. And number 3, what distances can you be certain of on ruler C? So here's ruler C, and if we look, there's a line for each ones place. So we can be certain of any measurements in the ones place. If you weren't in class to measure with ruler A, it would be tough to answer number 4, so we're going to skip number 4 and number 5. But I think we can do 6 and 7. So if you look at the rulers A, B, and C, which one do you think would have the highest precision? It'd be C, because there's the most lines on this ruler. And for number 7, which ruler provided the highest accuracy? Again, it'd be C, because there's the most lines on this ruler. Okay, so now we're just going to talk about some vocab that we'll use a lot. Okay, in your student sheets, you have a place just for definitions. So if it's written in red on here, red is the indicator that it's going to go on your student document. So whenever we make measurements, there's always going to be a little bit of error in that measurement. So the way we define an error is just like this measurement of bias from the accepted value in a result or in a measurement. So just, you're always going to be a little bit off from the true answer. And since there's always going to be a little bit of error in measurement, that means there's always going to be some uncertainty. So it's just, your uncertainty is just like a range of possible values for a measurement. And I'm going to circle back to uncertainty in a little bit later today. Bless you. Bless you. All right, and then when we measure, we'll talk about accuracy. So how accurate you can measure or the accuracy of measuring tools. So accuracy is the closeness of a measurement to the accepted value. Okay. Another way to think about accuracy is like how correct you are. Okay. So if you are measuring accurately, you're measuring the correct value. And then precision is just how repeatable is your measurement. So if you measure like the volume of the ball bearing, if you do it 3 times, can you get the same answer all 3 times? Okay, so in chem, we're going to talk a lot about accuracy and precision when measuring. So we're just going to define like, well, what's the difference between accuracy and precision? Okay, we want to be both, but what is the difference? So do you see where I underlined? You can shorten this up and just copy down the underlined. So accuracy is just how correct you are, and it can be one single measurement, right? Like I can measure the volume of the ball bearing once, and I can be correct, or I can be accurate. Okay. Precision has to require several measurements. It's like if I go measure the volume of that ball bearing 3 times, I need to get the same answer all 3 times. Okay, so I need the same answer multiple times. Another way to help us understand accuracy and precision, we're just going to use this dartboard as an example. If you're playing darts, where are you aiming? Okay, the middle, the bullseye. So on your page, you're going to draw X's with me. Go at my pace because I'm going to change up the second one a little bit. I think we can do better than like the set picture here. Okay. So our first example is, what does it mean to be not precise and not accurate? Okay. So if our target is the bullseye, if you're not accurate, you're far away. So do you see how all of these X's are not even close to the bullseye? Okay, so that's not accurate. And then precision is like if you're going to play darts, you would need to be able to throw that dart and hit the same spot over and over again. So these, do you see how they're spread out all over the dartboard? So they're also not precise. So then on your paper, you just need to like mimic the X's. All right, our second one is just showing what it's like to be accurate but not precise. If it's accurate, where should the darts land? Okay, towards the middle. I'm going to move the red X. I'm going to put the blue X there. I think if they're accurate, they need to be at, like closer to the bullseye. Okay, so they're accurate. They're close, right? But then they're not precise because are they close together? No, it's like they're still spread out, so they're not precise. The third one is precise but not accurate. Okay, so precise, do you see how they're all pretty much in the same spot? So that's precision, but then they're not accurate because they're not at the bullseye. And then finally, the last one, precise and accurate. Okay, so accurate, they're all in the bullseye, and then precise, are they all in the same spot? Good. So whenever we measure, there's always going to be error every single time, even if you think like this is the best measurement you've ever made in your entire life. Okay, there's always going to be a little bit of error when it comes to that measurement. Okay. So then in science, we'll calculate our percent error. Because let's say we're getting numbers. Let's say we're doing a lab and you're supposed to make like 5 grams of a product and you made 4.5 grams. Okay. Well, is that close? Is that not close? So percent error is a formula we use to figure out like, well, how accurate were your measurements today? Okay. So then on your page, you're going to copy down the formula for percent error. Okay. So it's the observed value. That's the one that like you would measure. And then you subtract it with the accepted value. That's like the correct value. And then you're going to divide that all by the accepted value and then multiply it by 100 to turn it into a percent. So in class today, we did this measuring practice where we actually calculated percent errors on some of the lines we measured in the beginning. If you were absent from class today, you're going to skip this section. So on your student document, you have this table that says observed value, accepted value, and percent error. Go ahead and skip that table and go to the next page. So now, maybe look at my screen. When I change to my software that records me, it kind of messes with my formatting sometimes. But on your page, you should have a line over a ruler. Okay. Does it hit at roughly the same spot? Like, does it hit in between 50 and 60 on your page? Okay. If it does, go ahead and read where the line falls on your page. If your formatting was weird and it's not hitting between 50 and 60, read it off my screen up here. But go ahead and, like, read the length of that line. And go ahead and just, like, write down, like, how long do you think this line is? Okay, how long did you think this line was? Like 56? Raise your hand if you said 56. How many of you said 55? How many of you said 57? Okay. Anyone else want to give a number out there? Okay, 58. All of those are fine numbers. Okay. So if we look at the measurement, do you see how we had a little variety in this classroom? Okay, so whenever humans measure, is there always going to be a little bit of variation? Okay, always a little bit because there's like this human perception that gets factored in, so there's always going to be this variation. However, there is some level of certainty when it comes to this ruler. Okay, so can we be certain that this line falls in between the 50 and the 60? Right, like would you all agree with that? That like this line is somewhere between 50 and 60. Okay. So we're certain it's in that range. And 50 and 60 is red. So do you see on your page you have like a fill in the blank to put 50 and 60? Okay, so whenever we're going to record a measurement properly, the measurement is going to include all the digits that we're certain of, meaning there's an actual like scale with lines on your tool, and you're going to include one digit that you are uncertain of, or you're going to have to guess a digit. That means you're going to have to read in between the lines. Okay. So when we measured, I'm going to go with 56 because that's what I wrote down. Are we certain it's at least 50 something? Okay, but then did we all have to take a guess on that second number? Okay, so we might have guessed 8, 7, 6, 5. Okay, this second digit is the guess. So from here on out, when we read a measurement, you're always going to do every digit you're certain of plus one last digit that you have to guess. And we'll do quite a bit of practice this week and next week. Okay. So let me show you some examples of valid readings. Okay. Any to the whole number. So you don't have to write all these numbers down, but a valid, like an accepted measurement in this case could be like 51, 52, 53, 54, 55, and so on. The reason why these are valid, we are confident that it's 50 something. We're guessing the second digit. Okay. So just write a couple of those down. You don't have to write all of those numbers down. Okay, and then let me show you some invalid readings of the line. So 56.7 would be invalid. Okay. The reason is we know the line was past 50, but are we even certain it's 56 something? Okay. We're not certain about the 6, so by writing 0.7, we're now guessing 2 digits, right? I'm guessing on the 6 and the 0.7. Another inaccurate reading would be like 56.98. Again, I know the 5, but I'm guessing on the 6.98. Okay. Another example, 56.999. You can't measure that far out because you only know the 5, so you're guessing the 6.999. Okay. So whenever we measure, you can only guess one digit. Okay, so then these rules of how we measure, we call them significant figures, or you'll hear me call it sig figs for short. Do you see where we get sig fig from significant figure? So significant figures is just all the digits in a measurement that are known with certainty plus one digit that's estimated. So on the previous slide, we said this line was 56 centimeters in length. Okay. Are we certain that it's for sure 50 something? We're certain about the 50. Did we have to guess on the 6? Okay. So that's all significant figures are. So it's all the digits I know with certainty plus one more that I'm estimating. Okay. So then when we look at measurements in science, we can count like how many significant figures are in a measurement. So if we measure this line to be 56, right now there's 2 digits, so there would be 2 significant figures in that measurement. Okay. When I see you on Monday, we'll talk more about rules of like, how do we know how many significant figures are in a number? Okay, but right now, 56 is just 2 significant figures. So then with that line we talked about, if humans are measuring, there's always going to be a little bit of error because you have to guess, right? We're always guessing that last digit. So if there's error, that means there's uncertainty in measurement. So to determine the uncertainty in the measurement, we just look at the last digit. And that uncertainty is just plus or minus the value of the last digit. So on your page, do you see where there's uncertainty in measurement? Okay. And I give you 24.2. Go ahead and write down this plus or minus part. Okay. So 24.2, what's the place value of this last digit? Okay, 0.1 or 0.2, but what's the place value of the 0.2? The tenths column, right? So then the uncertainty is just plus or minus a tenth because it's in the tenths column. And then go ahead and add what I'm about to add. So that means that the true value, what's 24.2 minus 0.1? Okay, so it could be 24.1 through, what's 24.2 plus 0.1? 24.3, okay? So your uncertainty is this range. So all you're saying is the true answer is somewhere between 24.1 and 24.3. Do I have a tool to tell you exactly where it is? No, like this is kind of the best I can do with the measurement tool I have, okay? But it's going to be in this range. Okay. Let's say your measurement's 32. What's the place of the last digit here? What place value is that? Ones. Okay, so your uncertainty is just plus or minus 1. So what's 32 minus 1? 31. What's 32 plus 1? 33. So it means that the true value of that measurement is somewhere between 31 and 33. Okay, the last one is 100.55. What's the place value of this last digit? Okay. The hundreds column, right? So your uncertainty is plus or minus 0.01 or 1/100th. Okay, so then what's 100.55 minus 0.01? Okay, so 100.54, and then what's 100.55 plus 0.01? Okay, so then this time, the uncertainty is somewhere between 100.54 through 100.56. Okay, so now we're going to practice measuring to the correct number of significant figures. This isn't on your page, so you just have to look on my page. So these are graduated cylinders. Okay. When we read the cylinder, you need to read the bottom of the curve. Okay, so the lowest point. And then do you see the black line? You could read to the top of the black line or the bottom. You need to read to the bottom of the black line. Okay, does that make sense? Okay, so the first thing we should do is figure out, well, what's the scale on this cylinder? So if this is 50 and this line is 60, what do all of these individual lines represent? Okay, 1. So we can count 51, 52, 53, 54, 55, 56, 57. Okay, so where does it look like the line is landing? Okay, does everyone agree it's definitely at 56? Okay, and then can we be certain it's at least 56? Okay, then we have to guess one more digit. Okay, does it look like it's exactly on the 56 line or a little above or below? What did you say? Okay, how many of you think it looks just like a slight bit above? Okay, you're going to have to guess one digit further. And if it's just a tiny bit above, maybe 56.1. And it's a volume, so we'd be milliliters. So this is what we've been learning about sig figs. So it's every digit we know plus one more. Okay. How many of you think it hit exactly at the line? Anyone? Okay, let's just say you did. I would also take, if you think it sits exactly at the line, maybe 56.0. Okay. That's fine as well. But you have to do the 0.0 because can we all agree it's definitely 56? Okay, so you have to go that one digit further. So this one has to go to the tens place. Okay. All right, let's look at the middle one. So start with the scale. So here's 3, here's 4. So what does each little line represent? 0.1? Okay. So here we're 4.1, 4.2, 4.3, 4.4. Okay. So what is it definitely? Like what numbers are we certain of? Okay. So we're certain it's 4.3 something, right? And then that line, it's in between the 3 and the 4. Okay. So then this is where you're going to have to kind of judge and guess on your own. Is it exactly, and remember you're reading the bottom of the black line, is it halfway between 3 and 4? Okay. I don't think it's, I think it's lower than halfway. If it was halfway between 3 and 4, what number would you put here? 5. To me, the bottom of it looks less than halfway, so my number better be less than 5. I might go like 4.33. How many of you did like 4.32? 4.34? 4.35? Are any of those okay? Any of those are fine. Okay. It just has to be every digit you know plus one more digit. Okay, I want you to try this last one on your own, and then we'll check answers in like 20 seconds. Okay, someone share a number with me out loud. What did you measure this to be? 23.9. Raise your hand if you agree. Give me another number.
23.8.
Okay, maybe 23.8. Raise your hand if that's what you wrote down. Okay, what could be another valid number? Maybe 23.5. Could you have 23.6, 23.7? Okay. So, do we all agree it's for sure 23 something? Okay. I might go like 0.6, 0.7. Okay. Do you all have something to the tens place? Okay, that's the key here. You need to have 23 point something. Okay. So, when we measure in science, we use the metric system. Okay, so no inches, no feet, no pounds. Okay, metric. And then if you look on your student doc, do you see it give you a little table of base units? Okay, we're going to fill in these base units. Okay, so in length, if we're going to measure the length of something, in metric, the base unit is a meter. Its symbol is a lowercase m. If we're going to measure the mass of something, the base unit is kilogram, and its symbol is lowercase k, lowercase g. Time is measured in seconds. Its symbol is S. Volume is in liters. Its symbol is L. Density could be grams per cubic centimeter or grams per milliliter. It really just depends on how you get that volume. So if it's grams per cubic centimeter, here's the unit or the symbol for it. And then if it's grams per milliliter, here's the symbol. And then again, temperature, it can be in kelvins or Celsius. Kelvin is just a capital K, and then Celsius is a degrees, capital C. Okay, so these are the base units of the metric system. So like the base unit for length is meter. But let's say I want to measure like the width of my finger. Is like 0.01 meters like a friendly number to use? Or it's 0.01 kind of obnoxious? Or maybe if it's like 0.009. So the nice thing about metric is we can use prefixes to get normal units, okay, normal numbers. Do you see the 3 in red? These are the 3 I want you to write down. They're the 3 we use the most often. They're the 3 you just need to memorize, okay? So let's say we want to measure something really tiny. We would use millimeters. The symbol is lowercase m, lowercase m. And then we'll start doing a lot of conversions, like between millimeters and meters. So you need to know the relationship. There's 1,000 millimeters in a meter. Okay. So here's our meter stick. If I were to break this up into 1,000 increments, one of those is a millimeter. Okay. The next one you just have to know is centimeter. Centimeter is little c, little m. And there's 100 centimeters in a meter. Okay, so like all the ones up here is a centimeter. And then finally, let's say we want to measure something really big, like to the distance to your house. Are you going to measure meters all the way to your house, or is that going to be an obnoxious number? Obnoxious, right? So big numbers, we might use kilometer or kilometer. So km. 1 kilometer is 1,000 meters.